1.13 is more of a coding exercise than an actual physics problem, but as in physics, if you ever plan to go down this field, there is a lot of programming, so I figured it would be useful to sort of cover this anyway. So 1.13 asks for us to check our results in problem 1.11b, where we defined our probability density for a simple harmonic oscillator, and we want to do the following numerical experiment where we define the position of the oscillator as a sinusoidal cosine function. From this point, we take omega and a to be equal to 1 for simplicity, so we get x of t equals simply cosine of t, and then we want to make a plot of x at 10,000 random times and compare sort of the occurrence of given points with the probability density function, and we're going to be doing this using a program. So just to start off right away, we're going to look at what rho of x actually looks like for a simple harmonic oscillator, and we did this in 1.11. It looks something like this, where our particle has a higher probability to sort of be along the edges of our oscillator, which is these are sort of near the turning points at positive a and negative a, and that logically should make sense. Our particle is more likely to spend more time sort of in this turning point area where it has very little speed compared to sort of the middle area where it has a very large speed, or even directly in the middle where it actually has the maximum amount of speed. So we will now sort of move on to a coding program to sort of code out this 10,000 samples that the problem wants us to do. Griffiths uses Mathematica. I'm personally more comfortable using using Anaconda and Jupyter Labs, so that's where I will be doing it on. However, sort of the process to do this is mostly the same. So you can sort of take the method I used and research out the analogous functions in Mathematica and do it that way as well if you want. Right, so this is Jupyter Lab. I'm going to sort of assume that you have at least some basic amount of programming knowledge, but otherwise I will sort of go over everything regardless. So first off, the thing that we do is we have to import all of these modules, math for the purpose of defining the cosine, we have to import random for the purpose of defining random samples, we import numpy because we want to use arrays for graphing, and then we import matplotlib.pyplot because we want to graph stuff. So these are sort of the four modules that we want. First thing that we're going to do here is we define sort of the function from which we pull samples from, which is f of t, and we're going to define it as just math.cosine of t. Math is sort of the module that we're importing from, so we imported math so we can use cosine, and here we're doing what Griffiths suggested, and we're sort of setting a equal to 1. Technically this is a cosine of omega t, but instead we're going to set omega and a equal to 1 as Griffiths suggests for simplicity, so our function is just cosine of t. Next thing that we're going to do is we're going to define our x and y axes, so I'm going to name them position and time. And then from there, sort of the next thing we do is we want to take 10,000 random samples. Now from here, obviously, we can't just have the computer randomly choose numbers from 0 to infinity. So instead, we can recognize that cosine of t is a periodic function. So because of that, anything past 2 pi is sort of the exact same thing as that number minus 2 pi. So instead of sort of pulling random samples from 0 to infinity, we can just pull from 0 to 2 pi. So here I'm saying that I'm defining a for loop in this range. So I'm basically iterating 10,000 times, starting at 1 and then going up to 10,000. And for each of these iterations, I'm defining a random value from 0 to 2 times pi, and this math.pi is because I'm importing the math module to define pi. So from 0 to 2 pi, I'm defining a random value each time for these 10,000 iterations, and then I add this value into my times list because this is sort of the random time I've selected, and then in the positions list up here, I add on the function of that sample time that I sort of added on, and this gives me my x and y axes. From there, if we want to graph it, we have to convert them into arrays. So we're going to do numpy.array, which is a function which converts our lists into arrays. And then from there, the first thing we can sort of do is we can try to plot a scatter plot of our positions versus times. And unfortunately, this doesn't necessarily help us very much, because this just gives us a rough outline of what the cosine function actually looks like. But since there's like 10,000 points, it's not exactly easy for us to tell where the points are showing up more often here, because everything just sort of is this mess of a line. So instead, the thing that helps us a lot more is to use a histogram. And if we use plot.hist, this is just a function that gives us a histogram given some sort of value or some sort of array. And in this case, we're going to use positions as our array. And if we plug this in, then we do indeed get a histogram that looks very similar to the probability distribution that we originally defined. Finally, we're going to sort of compare them side by side. So as we see here, evidently we have a very high probability of the particle being near our turning points, negative A and positive A, and a minimum probability of being close to the center where the particle sort of has the maximum amount of speed, and hopefully physically that makes sense. And our histogram sort of agrees with that. Our random measures of x have x appear a lot more sort of at the edges than it does in the middle. And sort of the biggest point that can be made about this is sort of this idea of probability, and the fact that we're defining everything in quantum mechanics in terms of probability. So because of that, a lot of these probability densities that we see really only make sense if we measure the system a large number of times. Because if I sort of just randomly decided to take maybe like 10 samples, I would not nearly have as agreeable of a distribution here compared to, in this case, where I made 10,000 samples. So really, I guess the way I interpret the reason why Griffiths gives this problem is sort of to re-emphasize the fact that quantum physics is very closely intercorrelated with the concept of probability, and that in many cases in quantum mechanics you really do have to take multiple, like hundreds of thousands of sort of measurements of a given system or copies of an identical system in order to sort of get the data to correspond with what you're actually mathematically describing, which in this case is going to be our wave function. Because if we measure just sort of a system once, what we actually measure is going to have no correlation with the wave function. Instead, we have to measure, hundreds of thousands of times to sort of create this histogram, which roughly agrees with our probability density and slowly begins to sort of agree with it more and more as we take more and more samples, just like in quantum mechanics, where we have a wave function